Hello, in this lesson, I'm going to review Chapter 5, Probability. This including Section 51, 52, and 53. Alright, so here in this chapter, we're gonna use inferential statistic, which use sample evidence to make predictions or generalization about our population. So the thing that we should do, we investigate questions such as the likelihood of a person winning a lottery table, the likelihood of getting in the car accident, the likelihood of that a prep course will improve a person's score on their LSATs. So we're investigating, we're using a sample evidence to make generalization about population. So one other thing that we learn in the chapter is the law of large number. It states that as a procedural experiment repeated again and again, meeting large sample size, the relative frequency probability of event is tend to approach the actual probability of the event. Now, when we consider event to be rare, if under given assumptions, the probability of a particular observed event is extremely small, and we conclude that the assumption is probably not correct. So, for example, if we assume that out of 1,000 coin tosses, there would be 500 heads and 500 tails for a fair coin. If we actually toss the coin 1,000 times and it results in 975 heads and 25 tails, we might assume that the coin is not fair, right? As the result would be unusual by pure chance alone. So these are some definition of terms in this chapter. So I would suggest pause the video, read them over. Now let's consider an example. So your book has another version of the sample space, like of tossing two dice. So note that this is one way to present the sample space of tossing two dice here. Notice that I use the sum of rolling two dice and possible outcomes here. Well, let's visit how many possible outcomes are there in the sample space. How to determine beforehand before you find all of the outcomes. So notice that here we can count them. Once you list out the sample space, you could count them here. So note that if you count this 1, 2, 3, 4, 5, 6, count total, you will see that it's 36. So here the sample space, number of outcomes in the sample space is 36. So there are 36 outcomes. So one way to determine how to find all possible outcomes is to use a table. So think of it as when you roll a die, you will have 6 possible outcomes. So let's say this is your first roll. You will have 1, 2, 3, 4, 5, 6. I can list them, right? And then in the second row of your die, you might still have 1, 2, 3, 4. Let me write a little more space. 2, 3, 4, 5, 6. Now you can list them the outcomes out. So for example, first one you might have a 1. Second one is a 1. So therefore your outcome will be 1, 1. First toss you get 1s. You also can get a 2 in the second toss. So 1, 2, 1, 3. 1, 4, 1, 5, 1, 6. So this is the possible ways of getting 1 on the first toss. Right? I can do the same thing. I can possible way getting 1 on the first toss. 2 on the first toss will be 2. 1, 2, 2. And you could list out all the outcomes in this one. Okay. So when you list it out, you will see that there's 36 possible outcomes. Note that if I see let's say 3, 3 here. Having 3, 3 here, meaning that you get a 3 in the first toss and also 3 in the second toss. Another example would be, let's say 5, 6, meaning that on the first toss you have a 5, in the second toss you have a 6. Right? That's one way to list all the possible outcomes. Let's find another way to list the outcomes. Let's say another method, let's use a tree diagram. So in a tree diagram, you can draw it, let's say on your first toss, you would get either a head or a tail. So first toss, either head or tail. In the second toss, you might have, for the head, you can have a tail. You do in the same order, head and then tail, right? If we have head on the first toss, maybe head in the second toss, also can get a tail in the second toss. Same thing here, I can do this way, head, tail, meaning that if I have a tail in the first toss here, then I could have a head on in the second toss, tail in the first toss, and then tail in the second toss. I can list the third way. Okay, so here I can do head, tail, head, tail, and then head, tail, and then head, tail. Now I can list out all the possible outcomes here. Let me use a different color. So I might have, you can read the diagram like left to right. So we head, tail is one possible outcome. Head, tail. Now you will have head, not head, tail. Head first. I'm listing the same order. Head, tail. I can also have head, tail, head. Head, tail, tail. Again, I'm following my diagram here. So head, tail, tail is this one over here. I'm following it. Let's do more. Next, I could have tail, head, tail. Tail, head, okay. Tail, head, tail. And I could have tail, tail, head. Tail. So now that this is the result, this part here, this is the first flip of a coin. When you flip a coin, or first toss a coin, first flip. And the red here is your second flip of a coin. Second, you flip the coin second times. And this part here is the third trial, the third time you flip the coin. Now notice that here, the list, when I write down all possible outcome here, this is just a sample space. We just found the sample space for tossing a coin 3 times. Okay? So this is called a tree diagram. Now tree diagrams, you can easily see all the possible outcomes. Now one of disadvantages is that if you have 6 possible outcomes, like you will flip a die, then the diagram can get really big. Right? So this is one way for it. Know that there are a total of 8 possible outcomes. 1, 2, 3, 4, 5, 6, 7, 8. You can also calculate it, the total number of outcomes, by using counting 2 to the third power. Oh, let me draw using a color. So 2 to the total number of outcomes. Could be a 2 to the third power, which is 8. Now, for each toss, you had 2 outcomes. That's why I have a 2 here. And you do the experiment 3 times. So 3 here indicating how many times you do the experiment. And the 2 here is how number of possible outcomes in each experiment. All right, so the total 2 to the third power, which is 8. So 8 possible outcomes. Now let's use that. Later we're going to use that to answer some probability questions. All right, let's use the general rule number 1 to find probability. First one is a classical probability. Classical approach to find it. That is equal that to find the probability, let E represent the probability of that particular event. Then that is equal to the number of outcomes in E over the number of outcomes in the sample space. In a shorter form, you can write it as P of E is equal to N of E over N of S. N of S meaning total number of outcomes in the sample space. Right? So let's use that to answer the following questions. 1. What is the number of outcomes in the sample space? We see the total number of outcomes in the sample space here is A. Right? So A possible outcomes. You can count them. Now here I list that in this form here, in the sample space form. Now other events independent. Well, think about it. When you toss a coin, you either get a head or a tail But whether you get a head or tail in the first toss does not change what you're going to get in the second toss. So the events are independent. Well, let's find the probability of rolling all three heads. Okay, let's look at my sample space here. Roll three heads is this one over here. Well, how many ways can you roll three heads? Well, notice that in the sample space here, one of them had three heads, so which is 1 over A. So probability of having a head on the first row, head on the second row, head on the third row is equal to 1 over A. Now later, we're going to learn to use the independent rule to calculate the probability without looking into the sample space. Well, let's look at number 4. What is the probability of rolling a head on the first toss, tail on the second toss, and head on the third toss? Okay, let's look for that in my sample space. So first toss, I want a head. So head, tail, head. Head, tail, head is this one over here. Head, tail, head. Again, this is only 1 over A again. So therefore 1 over A. So probability of having a head, tail, head. The second rule of probability is relative frequency approximation. So I can use the relative frequency. Relative frequency, we will learn that in chapter 3, which is equal to the frequency over the total number of times, right? So here, P of E, you can write that way. If E is equal to the relative frequency of the event, then P of E is equal to the frequency of E over number of trials of the experiment. You can also think of it as number if times A occur over number of times the trial will repeat it. I think of that way. So let's do an example. So this is a survey of a labor statistic here. So let's use that to answer the following questions. And we're going to pay particular attention to the N here. Later, we're going to use the N rule again from 5.3, but let's pay attention to the N. What does it mean in the table? So first, how many people responded to this survey? Well, the total number responding in the survey is this number over here. It's 208,720. Notice that if I would add the row totals here, 24,395, 61,441, add all this up, I would get this number. This is a grand total. And if I would add the column total, which is the 3 number over here, I also going to get this number, right? So when you calculate your totals in your table, you can check your answer by see the column total and the row total actually matching, right? Right? So let's answer the question. So we say there are 208,720 people in the survey. Number 2, what is the probability that a randomly chosen person was employed? Well, I'm looking for employed, so let me kind of highlight it. Let me use a blue color, employed. Employed is this row over here. So in the survey, not the total number of people who responded to the survey that indicate that we employed it is this number over here, which is the row total. The row total, and the row total over the grand total here gonna give me the probability. So let me write it. Okay, so I use the number here, number of times it happened in the survey over the total, and approximate it to 4 decimal places, 0.616A. So we'll say the probability that a randomly chosen person was employed was 0.616A. All right, let's do the next one. What is the probability that a randomly chosen person graduated from high school? Okay, graduated from high school, that is a second column. Okay, let me highlight it in different color. So this column here. So I'm looking for the column total in this case. The column total over the grand total. So 61,442 over 208,720. And let's round that to 4 decimal place. Okay, so we got 0.2944. I want you to be careful when you do a rounding rule here. Make sure do it correctly. And generally speaking, if in our handout here, if I don't say how many decimals, for probability, assume it's 4 decimals. All right, let's do the next one. What is the probability that a randomly chosen person is not in the labor force and did not finish high school? Okay, let me kind of erase the thing that we highlight here so we can do it again. So not too confusing. So let's think about it. First thing is I want the person that's not in the labor force and Okay, two conditions, and I want that person to be did not finish high school, right? So first, I'm gonna circle the row indicating the person is not in labor force. Okay, and that is, let me use color coding. Let me do color coding instead of doing circle and green. Let me do a blue for not in labor force, and then I'm gonna use green for not finishing high school. Okay, so not in labor force is the third row right here. Okay, did not finish high school is in the first column. Oh, wrong color. Did not finish in the label force, the third row, and I'm going to use green for not finish high school, which is the fourth column. Okay, so notice that the N tells me look for the intersection where the overlapping number here is 113,271. So that's the frequency, how many times it happened, right? So looking probability is the frequency it happens over the total. So that would be 13,271 over the grand total. And let's do it. Okay, and then we got 0.0636. Again, if I want to answer the question in a complete sentence, I would say the probability that a randomly chosen person is not in the labor force and did not finish high school is 0.0636. I can also interpret in the long run. If I want to interpret in the long run, notice I have 4 decimal places here, meaning that I can 10 times 10,000. Let me write it. So if I multiply 0.0636 times 10,000, okay, and then I would get 636, and I can interpret that saying that, well, if I would randomly select 10,000 people, I would expect to see 636 people is not in the labor force and did not finish high school. Again, let me say it again. So if I would select 10,000 people randomly, then I would expect to see 636 of those people is not in the labor force and did not finish high school. Okay. So when I say interpretation, and this is what I expect to see, so we can write it out. Right, so the probability that a randomly chosen person is not in the labor force and did not finish high school is 0.0636. That means if I was 10,000 people randomly selected, you can expect it to see that 636 of those people are not in the labor force and did not finish high school. Number 5 is the same as number 4, so let me just take that out. I think I meant to write interpretation of the probability getting number 4, right? This is the interpretation right here. So let's do number 6. What's the probability that a randomly chosen person is unemployed and did not finish high school? Again, I'm looking for the keyword here's N here, and I'm looking for unemployed and did not finish high school. Up to my table. First, let's unemployed. Try it again. So unemployed is the second row. Not finished high school. The overlapping number here is 945. So that means 945 people in the survey are employed and did finish high school. So for find the probability, we use that number over the total. So let's write it. Okay, so calculate round to 4 decimal place. I got 0.0045. And notice that the N again is the N, meaning I'm looking for the overlap on my table. Okay, let's answer question number 7. Is it unusual for a randomly chosen person to be unemployed and did not finish high school? Well, I think about in chapter 3, when we use the empirical rule, we said that an event considered unusual if it's outside 2 standard deviations of the mean. And here, unusual means an extremely low number. We consider unusual if it's under 5%. So let's look at the probability. So probability of that event, the event here, unemployed, let me write it out. Okay, so we said this probability is 0.045, which is under 5% or less than 0.05. So therefore, I said the event is considered unusual since it's under 5%. Again, here we say consider for under 5% will be considered unusual. Again, you really have to, when you think about unusual or not, look at the content of the application. Rule number 3 is subjective probability. So P of probability of event A is found by simply guessing or estimate its value based on knowledge of the relevant circumstances. Let's write know a probability here. This is general note. So the probability of an impossible event is 0. We say something is impossible. The probability of an event that is certain to be occur is 1. And we say probability of event for any event, probability is always between 0 and 1 inclusive. And the law of total probability for any experiment, when you sum up all the probability in the sample space, is always equal to 1. So for two events, when they are not disjoint, then P of A and B is not equal to 0. And notice that when I add this equation here, let me highlight again. So there's a P of A or B, we add them, take away the overlapping part once. The reason that we need to take away the overlapping ones because when I add P of A plus P of B, notice that region 2 has been added twice. That's why I take away one copy. So if I want to find P of A or B, P of A or B here, I can simply add up the total of 1 plus 2 plus 3. So again, 1, 2, 3 are relative frequencies, a probability of things in there. But region A represents things that are in A but not in B. Region 3 represents things in B but not in A. Region 2 represents region A and B. Right? Now, when events are disjoint, the probability of intersection is 0. Notice that there's nothing in common, so the joint probability is 0. Disjoint, another word for mutually exclusive events. Let's review section 5.3 a little bit. So two events, E and F, are independent. If the occurrence of event E in the probability experiment does not affect or alter the probability of F. Two events are dependent if occurrence of event E in a probability experiment affects the probability of F. Right? So when two events are independent, we can use the multiplication rule. So let's say E and F are independent, then P of E and F is equal to P of E times P of F. Now the multiplication rule in independent events says if the events E1, E2, or the En are independent, tend to find the probability of all of them, E1, E2, E3, all happen is equal to multiply them, like the product of the probability. So let's use the event, think about experiment of rolling a coin 3 times. Right? So let head represent the event of rolling a head, and T represent the events of rolling a tail. Okay, what is the number of outcomes in a sample space? We did that one in 5.2 by list down all the sample space. But we can calculate it as well. So to calculate that, think about it. When I roll a coin, and we have there 2 possible outcomes, right? 2 possible outcomes, and we roll that coin, we flip the coin, not roll a coin, 3 times. So 2 to the 3rd power are going to give me A. So there are 8 possible outcomes in the sample space. Now, now let's do part 2. What are the events independent? Let's think about it. If I flip the coin, whether I got a head or tail in the first flip, it doesn't change what I'm going to get in the second flip or the 3rd flip or the 4th flip. So therefore the events are independent. Number 3, what is the probability of rolling 3 heads? We kind of found that one is 1A in a sample using sample space, but let's think about it. P of head, when I flip a coin once, P of head is 1/2. Equal to head or tail. And so P of tail is also 1/2. Right? So that is for if I flip the coin once. Whoa. Now let's think about it. If I flip it 3 times, we know the events are independent. That means I'm finding the probability of having 3 head. Let me write it. I can write it using a notation. Head on the first flip, head on the second flip, head on a third flip. And since the events are independent, I multiply them. That's equal to P of head on the fourth flip times probability of getting head on the second flip times probability of getting a head on a third flip. Okay, getting a head on the fourth flip is 1/2. Probability of getting a head on the second flip is also 1/2. Probability of getting a head on the third flip is also 1/2. So therefore, that's equal to 1/2 times itself 3 times, so 1/A. So the probability of getting 3 heads when flipping a coin 3 times is 1/A. Number 4. What is the probability of rolling a head on the first toss, tail on the second toss, head on the third toss? Okay, let's write it out. The innovation. Well, I want finding the probability of first toss of getting a head on the first toss, tail on the second toss, head on the third toss. Okay, there's a probability of finding head, tail, head. Okay, the events are also independent. So therefore, that is equal to probability of getting head on the first toss times probability of getting a tail on the second toss times probability of getting head on the third toss. Okay, it's event independent, so for each probability is 1/2 here. That's why multiplication rule tells me I can multiply them. That's also 1/A. What is the probability of rolling a tail? Let's do one more. Yeah, writing probability of rolling tail on the first toss, head in the second toss, a tail, and then a head on the third toss. Okay, head on the third toss, and that is equal to, I think by now we should get it. Again, probability of getting a tail on the first toss is 1/2. Probability of getting a tail on the second toss is 1/2. Probability of getting a head on the third toss also 1/2. So I can also just write it as 1/2 to the third power, which is 1/A. This concludes our probability review. Thank you for watching the video. I'll see you next time.